Last time we met the perceptron, a single neuron. It could only ever draw one straight line, and that line hit a wall it could not cross. The exclusivo pattern, where no straight cut separates the classes. So here is the fix, and it is almost embarrassingly simple. Don't use one neuron. Use many, arranged in layers, each feeding the next. That is a multilayer perceptron, a neural network. And with a hidden layer in the middle, the wall simply disappears. By the end of this lesson, you'll know exactly how these layers compute, why one small nonlinear step is the whole secret, and you'll watch a hidden layer solve the very problem that stopped a single neuron cold. Start with a single layer. A layer is just several neurons sitting side by side, and every one of them looks at all the inputs. Three inputs on the left, two neurons on the right, and each neuron has its own weights and its own bias. Neuron I computes its own weighted sum, a row of weights dotted with the inputs, plus its bias. That's Z-die. Stack all those rows together, and the whole layer collapses into one tidy line. The vector Z equals a weight matrix W times the input vector X, plus a bias vector B. Each row of W is one neuron's weights. Then every entry passes through an activation G, applied element by element, giving the layer's output A. So a layer is exactly two moves, a linear map, then a nonlinear squish. Hold on to that pair. Now stack these layers. The input feeds the first hidden layer, whose output feeds the next, and so on, until the final output layer. Information flows strictly left to right. That sweep is called the forward pass. Watch it move. Each layer takes the numbers from the layer before it, runs its linear map and its activation, and hands a fresh vector forward. Light travels through the graph, one column at a time. And the whole network is that one recurrence repeated. The activations at layer L are G of WL times the activations from layer L-1 plus the bias BL. Start the chain with A0 equal to the raw input X and turn the crank layer by layer. Here's the question that decides everything. What if we get lazy and drop the activation? Let every layer be purely linear, just matrix times vector plus bias, with no squish in between. Take to such layers, biases aside for a second. The first gives Wuldufen times X. The second multiplies that by W2. But W2 times W1 is just another matrix. Call it W prime. Two layers collapsed into a single linear map. And no matter how many linear layers you stack, they always fold back down to one. Depth bought you nothing. Put numbers on it. 2, 0, 1, 3 times 1, 2, 0, 1 multiplies out to 2, 4, 1, 5. One plain matrix. The network can only ever be a straight line model, so it inherits the perceptron's wall. It still can't do exclusivo. That is why the activation is not optional decoration. It is the whole point. One non-linear bend between the linear layers is what stops the collapse and lets depth build genuinely curved, folded decision boundaries. The squish itself is one of a small family of activation functions. Three show up again and again. So let's meet them by shape. First, the sigmoid, a smooth S-curve that gently squashes any number into the range 0 to 1. Next, taha, the same S-shape, but centered on 0, mapping into -1 to 1. Because its outputs are balanced around 0, it often trains a little more nicely than the sigmoid. And ReLU, the rectified linear unit, the workhorse of modern networks. It is dead simple. The max of 0 and X. Negative inputs become flat 0. Positive inputs pass straight through unchanged. A single clean kink at the origin. All three are nonlinear. That bend, that kink, is exactly what breaks the collapse we just saw. Each one gives the network permission to curve. Let's turn the crank with real numbers on a tiny 2, 1 network. Two inputs, two hidden neurons with ReLU. One output neuron with a sigmoid. Here are its weights, its biases, and an input of 1 and 2. Layer 1 first, the top hidden neuron. 2 times 1 minus 1 times 2 minus 1, that's 2 minus 2 minus 1, giving z equals minus 1. The bottom neuron, 1 plus 3 times 2 plus a half, 1 plus 6 plus 0.5, 7.5. Now the real u, minus 1 is negative. So it clips to 0, that neuron is silent. 7.5 is positive. So it passes straight through. The hidden layer outputs 0 and 7.5 onto the output. It's weighted sum. 1 times 0 plus 0.2 times 7.5 minus 1. That's 0. Plus 1.5 minus 1, which is 0.5. Finally, the sigmoid of 0.5, which is about 0.62. And that's the entire forward pass. Inputs in on the left, a single number out on the right. Every multiply and add laid bare. Now the moment we've been building to, exclusivo. Positive when the two inputs differ, negative when they match. Plot the four corners and the classes sit on opposite diagonals. The exact pattern that beat a single straight line. Give it a 2-2-1 network. Just two hidden neurons with real U. Each hidden neuron draws its own straight line across the square. One line alone still can't split the diagonals, but two, folded together by the real U, can. Here are weights that do it. Both hidden neurons read the sum x1 plus x2, but at two different offsets. The output then combines them with weights 1 and minus 2 and a bias of minus a half. Run all four inputs through. Same inputs give an output of minus a half, negative. Differing inputs give plus a half, positive. The signs split the exclusivo perfectly. There it is. The wall that stopped one neuron, cleared by a single hidden layer. That folded, piecewise boundary is something no straight line could ever draw. This is the whole reason we go deep. One last idea, and it's a remarkable one. Suppose you want the network to match some smooth but wiggly function. This gray curve, say, with just a handful of hidden units, a handful of little bends, the network can only manage a rough, blocky approximation. It captures the gist, but misses the detail. But add more hidden units, and the fit tightens. More bends, more pieces, hugging the curve ever more closely. This is the universal approximation theorem in spirit. A network with even one hidden layer, given enough units, can approximate essentially any continuous function as closely as you like. Enough neurons, enough bends, and almost any shape is within reach. Your turn. Same little network as before. Really hidden, sigmoid output. But feed it a new input, 2 and 0. Pause the video. Run the whole forward pass, by hand, and find the output Y. I'll wait. Here's the walkthrough. The hidden preactivations. 2 times 2 minus nothing minus 1 is 3. And 2 plus nothing plus a half is 2.5. Both positive, so RealU leaves them alone. The hidden layer outputs 3 and 2.5. Then the output 1 times 3 plus zero point 0.2 times 2.5 minus 1 3 plus a half minus 1, which is 2.5. And the sigmoid of 2.5 is about 0.92. If you got roughly 0.9, you've genuinely got the forward pass. Trap 1. The big one. Forgetting the nonlinearity. Stack linear layers with no activation between them, and they collapse into a single linear map. Depth without a bend is depth wasted. You must keep an activation between the layers. Trap 2. Leaning on the sigmoid everywhere. Out in its flat tails, its slope is almost zero, so the learning signal shrinks to nothing as it passes back through many layers. That's the vanishing gradient problem, and it's a big reason RealU took over the hidden layers. Trap 3. Feeding raw, unscaled features. If one input runs in thousands and another in fractions, the neurons see a lopsided landscape and training thrashes. Standardize your inputs first. It matters more than people expect. And trap 4. Assuming deeper is always smarter. Past a point, extra layers can overfit or become hard to train without the right tricks. Depth is a tool, not a free lunch. Reach for it deliberately, not reflexively. Let's lock it all in. A layer is one weighted sum through an activation. A equals G of Wx plus B. A linear map, then a nonlinear squish. A network just chains that rule. The activations at each layer are G of that layer's weights times the previous activations, plus its bias. Run it left to right. That's the forward pass. The nonlinearity is the whole game. Drop it, and every layer folds into a single matrix W prime, a plain linear model that can't even do exclusivo. Keep it, add enough hidden units, and the network can bend itself to fit almost any function at all. One neuron drew a line. Layers of them carve whole landscapes. That is where deep learning begins.